So the topic is around model visualization, and my primary interest is around data visualization. So I kind of work in the intersection of data, visuals, and stories. And I gave a talk late last year at Strata, Singapore, which was really around visualizing multidimensional data, and especially of interest to many data scientists in terms of how to visualize large dimensional data. And I wanted to kind of build on that and really explore how we could take these concepts in data visualization that many of us probably are familiar with and take it to as we build more models and machine learning models or statistical models and try and see how we can translate that. So that's kind of the crux. It is some thoughts around that, and I would probably go through this at a rapid clip, but we can be interactive, so if anybody has a question, I'm happy to kind of stop in the middle and answer. It can be a dialogue if possible, rather than just a monologue. So we don't see things as they are, we see things as we are, right? And I want to start with a story, right? Just to kind of build this concept up. How many of you have heard of the blind man and the elephant story? Okay, roughly 30–40%. So the story, and it has been told in many cultures, but I'll kind of quickly paraphrase for those who may not be aware of those. There are these 6 blind men, and they have never seen an elephant, and they want to see what an elephant looks like. And they're brought to an elephant. And the first one grabs the elephant, and he grabs the sides of the elephant and feels it and says, looking at the sturdy side and feeling like a wall, says the elephant is definitely like a wall. The second one actually grabs the trunk and seeing it sway, says this is definitely like a branch. The third one grabs the tusk and seeing it being very smooth and very round, says an elephant is definitely like a spear. The fourth one grabs the ear of the elephant and seeing it move around and being very flappy, says an elephant is definitely like a fan. The fourth one goes down on his knees, sees the elephant's foot, sees it coming out of the bottoms, looks at it and says definitely an elephant is much more like a trunk. And the sixth one, and the fifth or sixth one, by the time the sixth one comes, the elephant has turned around and it hits him with his tail. He grabs the tail and definitely looks at it and says, okay, or doesn't look at it, but feels it, and says an elephant is pretty much like a rope. So all these men of Hindustan disputed loud and long, each in their own opinion, exceedingly stiff and strong, for each was partly in the right, and yet all were in the wrong. So in our case, we are primarily working with data. And what the story kind of brings us is also, for us, the data, to a large extent, is the elephant in the room. And what we're trying to understand with this data is understand the process, the system, or a phenomena that is happening. And the data is one possible clue to that end truth. Our idea is to use that data and understand that end truth. It's a clue. There are many truths, and the data can provide us one clue to it. The men, or human beings, in this case, not gender bias, is really building models, right? And the model is, again, in very case, probably wrong, but could be useful. And the idea is to arrive at a point where the model is actually useful enough that we can understand something about the data, or something about the data and hence something about the phenomenon. So to think about this, there is a wonderful way to think about how do we go about looking at this. And there are this concept called the ladder of abstraction, in which once we're trying to understand a system, we're really trying to go up through these ladder of abstraction. We're trying to look at the data abstraction. We're trying to look at then the visual abstraction of that. And finally, trying to build a symbolic or a model abstraction of that. And we're not trying to do that in a very linear fashion. We're trying to do it in a ladder, and we may go up and down the ladder, right? So Brett Victor has this wonderful article called Up and Down the Ladder of Abstraction, in which he's trying to understand, let's say, a very simple self-driving car, where the car is trying to drive around a bend. And The first abstraction is really trying to model one possible way the car could travel, which is basically if it's moving on the center line, if it deflects by a particular degree, it comes back to the center line and at every pixel movement. And you can see the first ladder that you can see the path that the car would probably go on. The second level of abstraction on top of that is how all these possible paths could look like, depending on the degree of angles that you would choose. And the third level is given a degree of angle that the car could be navigating and possibly the bend degree, there's possibly a third level of abstraction in which you can understand how, in which cases the car would successfully able to navigate this whole space or not, right? And what visualization allows us to do as we go on up and down these ladder abstraction is really build a better understanding of how the model looks like. We may have a very simple model, in this case, just deflecting 2 degrees or 1 degree from the center and coming back to it. But by moving up and down this ladder of abstraction, we can have a better understanding of how the model behaves and how the model can actually play out as we look at the phenomenon, right? Wonderful article. If anybody's never seen it, go to Brett Victor, worriedreading.com, and you can look at this. It's an interactive piece, very nicely done. And the idea is to take this concept and see how we can apply it to what we may be doing in statistical modeling or data science, right? So why build models? Models are great because they help us explain the first level of ignorance. If I know what I don't know, I can model it. And modeling is great because it scales very nicely. And once it scales nicely, I can apply it to across a large set of data sets. Why do we want to then visualize it? Because visualization helps us kind of solve the second level of ignorance, which is I don't know what I don't know. If I don't know what I don't know, I need to see it. And I want to visualize it. And hence, if we can combine modeling the symbolic abstraction to a visual abstraction, we can probably get a better understanding of how this link is happening. So this is for any system that you're trying to model, but let's translate it to a machine learning speak because we're in a data science or a big data conference. If I translate this to machine learning speak, those abstraction layers become basically data transformations, visual exploration, and model building, right? And anybody who's done data science or any analytics, for example, would know once you frame the problem, acquired the data, and refined it, you basically have this pipeline in the middle which you operate around. So you do the data transformations, not one, because the data that is measured in may not be the best way to actually explain the process. So you do some amount of data transformations. And then you visually explore it, which is data visualization, which is primarily the space I work in. And then you build model around it. But if you notice this, the link between these two is missing. We do data transformation, we go build we do the visual exploration, then go back to data transformations and do the model building. What we need in a machine learning pipeline is basically add one more layer, which is, can we take our tidy data and translate it into something which is like tidy model, tidy model, and hence start to do visual exploration on the model that we built. And that would be kind of like the enhanced ML or an analytics pipeline that can actually help us to combine visualization not only at the data level, but at the model level. Right? Does that make sense? Okay. The key idea is to translate the implicit knowledge that I may have on my head around how the data works and bring it explicitly into the model. And the visualization is just a tool to help us do that, to see when the model is actually doing that, when the model is not really doing that. That, in hence, is the key concept behind it. And we can actually look at it in many different ways to see how we can do that. Like with data visualization, there's not one technique to do it. There's probably a set of techniques that you need to kind of think about. But if anybody who's done analytics could look at this, there are probably 7 steps that you would need to look at when you try and look at Model-Vis. And I'm calling it 7, even though the first step is really visualize the data space, because that's step number 0. You probably have done data visualization to kind of look before you can start to visualize the model. The second step would be visualizing the predictions, and you want to do it actually the predictions in the data space if possible. The third is to then look at the errors in the model fitting. So you've done the data space, you looked at the predictions that, now you want to look at the errors in the model fitting. And since you may not have one singular model, you want to see how the model behaves, which is you may want to visualize the model with different parameters. You may want to also look at how the model behaves when you give it different input parameters. So those two aspects. And then since you may not build one model, you want to look at how the entire model space works like. Once you've done that, you may actually find that there are probably some more features that you want to bring in. So you may have started with a selected feature space. You want to look at how I can visualize the entire feature space around it. And the final step, which may or may not happen, is you may not build one singular model to explain the whole prediction. You may actually build many models, or many models to explain part of the predictions, right? So you go from step 0 to step 7, and you probably do some of them, all of them, in a linear fashion, in an iterative fashion to explain, right? Now, if this is fuzzy, let me take some examples to make it concrete, right? So I'm going to take 3 primary examples to kind of illustrate how this concept, what the concept is and what the challenge in doing this is. So we take a regression example, a very small example, let's say a toy example to kind of build the case. We look at a classification example with a large P. P in this case is the number of dimensions. And we'll look at another regression example but in this case with large N. So large number of observations. N being number of observations, P being number of dimensions. And these are the concrete data sets. So there's a very simple cars data set we look at where N is around 50. Digits, which is kind of the MNIST data set where the dimensions are very high, and a taxi data set which has more than 10 million data points, right? So let's look at the small one to begin with. In the cars data set, this is pretty much a very simple example of a cars data set. We're basically trying to predict price versus kilometer per liter. Many of you may have played around with it, but in this case, this one's scraped from India, because that's where I come from. And so it's the Indian petrol cars with less than about 100,000 cost, or less than a million, less than a million, and we have about 42 data points, right? And this is one car, price for one car. So this is how, let's say, the 10 elements look like. The smallest car in India, or probably in the world, Tata Nano model, about 200,000 INR, 23.9 kilometers per liter. It's a hatchback with a very small engine, which is 38 horsepower. And the largest one in this case is a Volkswagen Vento, 785,000 INR, 16 kilometers per liter, a sedan with 104 bhp. So a very simple data set to kind of bring those concepts across. So let's go through those 0 to 7 and see if we can understand them. So visualizing the data space in this case, and let's start with only the 2 features, price and kilometers per liter. And you can look at the visualization. In this case, it's just a scatter plot, and we can try and understand, okay, this is how the data space looks like. And we can try and fit a model, and we can start with the simplest possible model in this case, which would be, let's say, starting with OLS, so an ordinary least square. And we plot the lines, and we can see now, okay, so this is the prediction space that we're trying to do. So we're mapping it onto the prediction space. We want to visualize the errors in model fitting, and the deltas between those are the errors that we're trying to visualize. And now you can obviously normalize it. You can look at it different ways, but we'll stick to one view just for ease of understanding. Once you visualize the error in model fitting, you may actually want to understand how the model behaves with different model parameters. So we started with OLS, but we may actually want to do a ridge regression, and we may play around with the alphas in the ridge regression to kind of see how the lines change or what the model fitting changes like, right? You may also want to go on to the next step and look at how the model will behave when we change the input data set. And in this case, we can take the same 42 models, bootstrap it, take a sample of it, and fit a line to it, and run it 100 times, 500 times, and try to see what the bias and variance in this model is. So this is a ridge regression But with bootstrapping, we can start to see what the model space looks like with the same model with different input parameters. How does that look like? Now, you may not build one model. You will build probably 3, 4, 5 models. So you may start with an OLS. You may add a ridge regression to it. You may then decide to fit a lowest to it or a polynomial of the third degree. And you have 4 models that you're trying to fit to it. And then finally, you would actually do what many of the machine learning teams will be doing now, which is to ensemble it and try and fit an ensemble model, which is basically, in this case, just an average, just a voting method. And so the thick line in the middle is kind of the ensemble model that you've got out of it. Right? But you may not stop at it. Now you want to visualize the entire feature space. So we add 2 more features to it. We want to add the hatchback and the sedan. So let's say the sedan is on the top. And we can, and this is clear to see because we're really missing the points on the top. So we can see that now we add the sedan, and we can see the blue ones are on the top, the hatchbacks on the bottom, and we can size the circle according to the horsepower. So we added all our 4 features onto the space. And obviously, looking at this, we may not want to build one model, but now build 2 separate models, one for hatchback, one for sedan. So we pick 2 separate models. We pick 2 separate models, and we fit a lowest curve to it. And we start to see we're starting to get better accuracy at the sedan level. And also probably pretty good now with BHP added into it, even at the lower level. Right? Simple regression, but these are the 7 steps that we would probably end up doing for the Model-Vis. So we visualize the data space, predictions in the data space, error in data fitting, error in model fitting, visualize with different model parameters, visualize with different input data sets, visualize the entire model space, visualize the entire feature space, and visualize the many models together. This is not new. Maybe I've just put it on structure, but this is what you all do, or at least some of you may be doing as you apply it to machine learning. So each of them has a direct congruence to what you do in machine learning or in ML. Data-vis is what we do in the data space. Mapping the predictions is the prediction in the data space. Validations, and including cross-validations when we're trying to look at the errors in the model fitting. Tuning is what we try to do with different model parameters. Bootstrapping is what we do with different input data sets. Feature engineering, ensembling is what we looked at, which is when you start to look at the entire model space. Feature engineering, when you're trying to pick out what the entire feature looks like or which features. And the last one is not so common, but is a common problem when you're trying to build many models. So you're in a retail store and you want to build a model for every SKU by every store level. You're trying to build many models that kind of explain that, and that's kind of like the end model approach. Right? So each of this has direct congruence to this. Does that make sense? Are there any questions so far? Okay. So in all of this case, even though I have talked about this in a very linear fashion, it's really iterative how you would approach doing this. And you would also do, as I talked about in the ladder abstraction, not only do it at the same level, I try to keep the view same so that we can talk about all this 8 steps, but you may actually go up and down the ladder abstraction to summarize in some cases at summary levels, or go down at the data space level and move up and down the ladder rather than just laterally, right? And even though I've seen a lot of my data scientist friends who never touch data visualization when they come to model evaluation, they would be largely sticking to numerical summaries and scores to actually do that. I, being a visual person, prefer to be on this end of the spectrum. I'm not saying they are mutually exclusive. They are most likely complementary. And even the most visualization unfriendly data scientists would still be trying to do some model score visualization at the minimum to evaluate how the model works. Right? So we move through these square layers to try and do that. And this is a simple example, but the challenge in doing this, like with data visualization, comes from 3 key challenges. The first is, and I'm calling them P, N, and N challenge. So the P is really when you have high dimensional data. So what do you do when the dimensionality of the data really goes up? What do you do when the number of observations become large? And what do you do when the number of models really become large? Because in a simple example, it's easy to understand this, but in each of these cases, it's really hard to see how we could extend this concept. So I'm going to take, let's address the first one, which is high dimensional data. So take a very simple standard data set that everyone may be familiar with, MNIST, which is digit recognitions. And to simplify the problem, at least for this, we will just look at two-class problem. So we'll just look at identifying 1 and 2 in the digits as opposed to all of them. And the P space in this case is large. So it's about 784 features because each of the feature is a pixel of 28 by 28. And we're trying to understand what the digit recognizes are. And we're about 5,000. So the data is not large, 5,000 data points. For those who may not be familiar with the MNIST, this is how it will look like. So if you basically handwritten a 1 and a 2, so 1 would look like this, and each pixel basically gives you a score of gray score where something is, the intensity of the color is largely black, so it's a largely sparse matrix, but some of them, where there's 1, you can make out that it's a 1 written slanting and there's a 2 written slanting. Now, we could first simplify this, and we can visualize the entire data space. So we can map all the rough 5,000 numbers onto it, and this is how the visual space would look like for 1 and 2s, and even with mapping all of them together, we can start to see the pattern is there in 1 and 2, right? So we can still make out 1 and 2, and it's a simple illustration, but we can also look at there is a symmetry and intensity in it. So 1 is obviously less intense than the 2, much more pixels are there, are glowing in 2 as opposed to 1. And there is also a symmetric dimension in which we can actually figure out using rotation and reflections and pick out. So we could actually summarize this 756 features into 2 for the moment, and we come back to then how to visualize it in the larger space, right? So we could just look at symmetry and intensity on the 2 axes, and now we can clearly see the 1s are on the bottom, highly symmetric, less intense, and the 2s are on the top, right? And so this is now we've reduced the P space, so we're not really answering the question, but let's begin with this analysis to kind of answer that question. So we can visualize the reduced feature space, and then start to map the predictions on this. So now prediction in this case is prediction probabilities, and we can see that obviously using a simple logistic regression, we can see where the errors are, which are largely in the middle, right? So we can visualize how the predictions look like. What we're really keen to understand is really the prediction boundaries. And this is a concept of doing meshes in which we kind of take the entire data set range and create a mesh and apply this mesh to kind of understand how the whole space looks like. And this will work fine for at least feature spaces which are up to 2, 3, 4, maybe even up to 10 P. So up to 10 spaces we can. And this is one of the most common approach that I saw when I started to look at model visualization. So Hadley Wickham has a very nice paper on model visualization, where he basically looks at meshes as a way of understanding how the space is, meshes with some amount of rotation, right? And this meshes is great, so we can visualize the errors in the model fitting. We can also start to do different model parameters on it and start to see how the errors look like, right? But the challenge with mesh is basically that is still in 2D space, sorry. So if you want to go back to our error space and say, okay, this is how will the visualization look like if we were to map our errors onto the data space back again, and this is the whole data space. We can start to see that the ones that are really not being picked up are the ones that are too much slanted. That makes sense. And the ones that 2s that are not really getting picked up are the 2s which are really symmetric in this case, or 2 written in a way that looks much more symmetric because we've summarized our features into symmetry. And in this case, we're lucky that we can visualize the entire data space in the 756 features in this case, in this one projection, if I was to say. So to overcome this for cases where we do not have projections, where we do not have simple ways to look at it, we need to really look at projections. So meshes are great. Meshes will scale very fine for looking at this model visualization for up to, let's say, about 10 features. But anything above that will be computationally expensive, and you need to then look at projections as a way to kind of look at it. So if we were to then reduce the 756 feature space into a projection, and in this case, just a PCA projection, we can start to see the separation in this case and start to map the errors on it, and start to see which of the errors that are not helping us understand the model or which of the errors that are not really answering the model, right? And projections will work fine as long as a projection is just a coordinate transformation. So we could actually do a TSNE projection for this whole space, and that would map very nicely and show us clean boundaries. But since it's a stochastic projection method, we can't really use this to understand our train and test data sets, right? So we need a projection that is fixed in nature, which can help us understand the features and then understand the errors on top of that, right? And the challenge here is really around, once you do the projections, how do you pick up the classification boundaries, and how can you then start to look and test and train errors on this? Not a lot of work has been done in this area. There is one interesting project on high-P boundary classifiers based on the scikit-learn, built on top of scikit-learn, which really looks at, with different models, parameters, so heavily regularized model versus less regularized model, what happens to the errors, what happens to the training data. So when is the model itself not working, and when is the training error not really working, right? It's still very experimental, but the idea basically is to get a boundary using data points on two ends of the spectrum, where the probability of classification is very low, sample it, and then take a sample of the data set and project it back on it, and sample of the test data set to project it. The idea, again, here is not to project all the data back, but to get enough clues that I can make an understanding about where the model is failing, what the model is not working on, and build that back into my model understanding. Right. Does that make sense? So all projections, anything in visualization, even if it's 3D, is always a projection, right? So any projection is a two-dimensional projection, as long as a projection is a transformation. So you have a dot transform function that you can apply. You can apply it to your prediction space, and then when you test it, you can apply the same thing back onto the prediction space and see how the errors map to it. So something like PCA or any of those techniques which are geometric transformation will work very fine with this. However, if you use something like stochastic, because it's really dependent, it doesn't have a fit transform, it's random seed generated, it's really hard to use this technique to apply it. So for example, in this high-P boundary classifier, they have a limited set of transformations that you can use, and that will allow you to kind of look at this. Right? Any others? Okay. So this is high-P. Let's look at the next challenge, which is really around what to do when the visualization number of observations really become high. And since we're in New York taxi trip data is a good one to look at. It's about 10 million data points for just 1 month. And not too many features, and we probably will use only 1 or 2 of them, basically the drop feature. And the idea is basically we're trying to predict whether you'll get a tip or not once you dropped at a particular point, depending on the time and geography of the drop points, right? And number of passengers in the car, right? So a very simple data set. And the large N challenge in model visualization is actually a very basic challenge in data visualization itself, right? So plotting itself is really hard. Visualization is great because it helps us to see the pattern, but visualization is something that doesn't scale very well as modeling does, right? So you can try to plot all the data points, but even with sampling, even with alpha treatment, you won't be able to get any visualization with more than 1 million, at 1 million data point or 10 million data points. You can sample it, And sampling is probably one of the good techniques to look at, as long as you can sample with some tuning parameters which take care of outlier data and then sample the data set so you know that the data set is representative. But it's a hard problem to solve. And so you would have either an overplotting problem or an undersampling problem, right? And the only way to solve this is really go back to kind of data visualization and see what the data visualization looks like. And the trick in data visualization is really around binning, right? So a huge plotting all the points is really hard, but if you can bin them in sufficient fashion, you can actually reduce the data space dramatically and then plot those bins around that, right? So there's a very lovely paper by Hadley Wickham called Bin Summarize Smooth, which takes just a MacBook Pro with 16 gigs of RAM and 10 million data points and shows how to do that. So how do you choose the binning? How do you look at smoothing and, summarization, which one of the summarization techniques will work? And then how do you smooth it using some kind of kernel smoothing to get a visualization, right? Really nice, done, 2013. There's also a package in R called BigViz, which takes care of some of this. Not probably on CRAN, but it's still workable. And obviously, there is now a Python implementation on similar process, aggregation, projection, aggregation, and transformation done by the Boca guys called Data Shader, which allows you to actually look at this same, right? So if you were to visualize the data space again, now and this is using the Data Shader library, and I've just simplified the data and plot the probability of getting a tip. We can start to see that probably the patterns are much more easier to see. You probably get much more in lower Manhattan, probably a lot around where we are, or not where we are, but Times Square, Central, maybe the tourist places, I know. So you can start to see the patterns that are really around that, right? And once you get that visualization problem solved, then you can do anything on top of that, right? So you could build a simple model, in this case, a very simple linear model using drop coordinates, passenger count, time and day of the week, and predict the probability of getting a tip. A terrible model. And as you can see, the probability is probably much more related to the longitude rather than the data itself in this case. But even with a simple model, once you have solved the data projection problem, you can apply it. And you can start to apply the errors in it and start to see how much the errors are really being explained or not, right? So the large end problem is largely around figuring out a data visualization bin summarize smooth kind of technique that can help you solve this problem, right? Once you've solved that problem, you can then visualize the errors in the same way that you would visualize in any other case and try and build on top of that, right? And this is on a geoplot, but the same challenge will be there even if you plot it on a X and Y2 axis, right? Okay. Yeah. Yeah, so in this case, so any error metric could be used to visualize. In this case, I'm just looking at what was the probability actually here, what is the probability in the prediction space, and the difference between the two. Yeah, so the actual minus predicted in this case and trying to see the error. So like we would do any error metric, in this case we're like looking at error metrics and saying where the error is. And not a great example, but in this case the errors are probably very similar to the data because our predictions is not really a great model, right? But you could translate it, and that's one of the other challenge in Model-Vis. It's not so much as the same way in visualization. The good visualization is not a standard set of charts, it's basically what fits with the data and domain that you have, right? So in this case, a geo visualization may be good. You could actually just do it on time of the hours also and see a visualization in a simple 2D way. So the visualization that you may choose actually will end up depending a lot more on the data and the domain, like in any case you are. But the challenges of whether it's a high feature case, whether there is a high N case or high number of observation is something that this would solve in either case, irrespective of the choice you make around that. Right? Yeah. Okay. The last challenge is really around N models. And even if you start to do this in a very simplistic case, there is a model explosion problem that really starts to come very quickly. So even keeping track of one model is really hard, but you now have 5 models or 10 models that you want to look at. Plus, you may have tuning models, bootstrap models, cross-validation models. And what we want to do is to, for each of this model, be able to keep track of the predictions and the errors and keep track of what the model output parameters is, right? So that entire space needs to be captured in some way. And that really becomes a very quick problem. Now, I'm fairly new to this. You can probably write your own code around a lot of this and create your own pipelines and wrapper to do it. But in a very structured library fashion, there are very few tools to do this, right? So the concept, the ideal solution to this is basically to convert each of these predictions and errors back into your data frame or wherever you're storing as back into the data set. So you want to augment those prediction and errors back into your data sets. And you want to find a way to also augment and keep an output parameter data frame that keeps track of all of this, right? And once you've done that, you can then visualize it pretty much like a tidy data. Because now you have it back in a tidy data sets. And this is the concept of tidy model. So the concept of tidy model is really trying to augment the model predictions and errors and whatever other output parameters that you want to store so that you can start to build it back again and use it to do visualizing the model the same way as you would be visualizing the data. Right? Now, there are two, I won't go too much into detail in this, but there are 2 great talks that anybody can look at. Managing many models in R is a talk, I think earlier this year by Hadley Wickham on how to actually store a data frame in R and then try and I think he has a package called Per that's written around to do that. And the other one is really the Broom package in R, which allows you to do this augmentation and allows you to do this augmentation in a very structured manner in R, right? And somebody's now written a package in Python which builds on scikit-learn and that builds this again. So PyBroom is a very similar package on that, right? So the 3 challenges in Model-Vis really around P, N, and N, high dimensional data, large and big data, multiple models. How do you solve that? So use projections for P. If you have large data, use binning, or in most cases sampling. There are very few large data problems. Most large problems are small data problems hiding in large data, so you could use sampling to do it. And if you have a large number of models, use tidy model to do that. To summarize, I guess Model-Vis, very similar challenges to data visualization. Again, pretty much an art than a science. So there is obviously a science behind it, but you need to figure out the data and the domain to make it work. I would suggest it to be an essential part of everybody's model pipeline. Even if you're not doing it, to find ways to do much more of visualization on the model side. And it can be used both to explain and predict, right? And there's obviously scope for easier tooling around that. So if anybody's interested to write much more around that, that'd be great. The slide and code for this is available on this website, model-vis.amitkaps.com. There'll be much more details around each of this coming by the end of the year on that, but the slides are available on this. And that's it. You can find me at amitkaps.com. Tweet me at amitkaps. I'm pretty much amitkaps everywhere. And if you have any questions, we can take. We have 1 minute. We have a minute. You can take it after. Yeah, sure. Okay, thank you so much.